Hello and welcome back to lesson 4.8. I've put the L at the end now, so it's 4.8. Actually, I just put lesson, because even in Skyward, it'll at least show that much at the top of my columns. Alright, so we're going to skip this page, although you should do it if you have extra time. And then there is this one that 6th period has. There's some nice things about 6th period's spirals, like they have little pictures of origami. But then, the layout is not quite as nice compared to this one. And look, they did things like in the new edition that most people have, they actually put the 90s in, but 6th period doesn't have the 90s. But there are blessings in all things. So we're just going to jump in straight in here at page 88. And for you weirdos in 6th period, it's page 42, which is the answer that we're looking for. Okay, let's get started, because I know you guys are already bored. Draw a right triangle with the acute angle that measures 60 degrees. How do you do that? Well, first you start with a dot. Then you put this dot on this. And then you put a dot here at 0 degrees. And you put another dot here at 60 degrees. There's the 60. You could also do it over here at 60 degrees, but then your triangle will be on the other side. I don't want it over there. I want it over here, where I put it the first time. Now this, you just need a straight edge here. And voila. Now, don't finish this triangle, because that's not a right triangle. We want a right triangle. What I'm seeing finish is don't connect this. Instead, pick somewhere along this line to stop this side. Pick somewhere random along this line. Okay, not over here, but somewhere in between here and here. Here. You can pick wherever you want. And then make a 90-degree angle up to the line. There's 60 degrees. That's my triangle. Okay, I can throw away the rest of it. And everyone will have a different size triangle. Amazing. Okay, and now we're using the 60 degrees. We're going to measure each side of the triangle as accurately as we can with a centimeter ruler, even using millimeters. Using the 60-degree angle. Oh yeah, this is a good time to say that you have to watch the other video first. Have to watch most important video 1 first. You have to watch the most important video number 1 first, and do the little first assignment and first assignment plus, which is like a quiz, and then do this, because there's words we're about to be using that I'm not going to teach you, because I already did teach you in the most important video number 1. Okay, now that you're back here, using the 60 degrees angle as the angle of reference, list the measure for each of the following. What's the adjacent side? Okay, adjacent. Well, first of all, we have the hypotenuse here. Hype. Adjacent's down here. Man, I'm erasing so much stuff today. I'm past my erasing quota. And then this will be the the opposite of 60 degrees. Opposite of the 60 degrees reference angle. So first I want adjacent, I'm going to say 18 millimeters. Length of the opposite side, using the 60 as the reference angle. 34. And now we can actually use Pythagorean theorem to figure this out, or measure it ourselves. 40 millimeters. According to Pythagoras, 18 squared plus 34 squared equals 40 squared. I can do 40 squared, that's 200. 18 is 200 something, I can't remember. Pause. I was wrong. It's 324 plus hey guys, I made a mistake. 1156 40 squared is not 200, it's 1600. What was I thinking? That's insane. I think I was thinking of 20 times 20 is 400. Ah! I ate too many fruit snacks. What was this, 324? Yep, checks out. 300 plus 100 is 400. Wait, does it? And 56 plus 24. Okay, so those two things added up is 1480. Square root 1480. 38.47. So because I was measuring it with a ruler, I was off. But that's okay. We're just approximately correct today. But still, 38.4. I mean, that's pretty close for measuring with millimeters, I think. Now, we're going to build these ratios. The opposite side. Okay, first of all, you are going to have different numbers. So pause the video. Pause and make your own triangle and measure it. Okay, and then come back here when you're done. Okay, you better have done it, because this next part's cool. And it's not going to be cool unless you have your own numbers, because we're going to figure out the decimal approximations. That's the approximate symbol. Okay. .85. So I took the opposite side, 34, and divided by my hypotenuse, which is 40. I got about 80.85. I could take the adjacent side, which is 18, and divide it by the hypotenuse, and I get approximately 0.45. And I'm going to take the opposite of the reference angle and divide it. What did I do? I screwed something up here. The adjacent is 18. Whoa. Good thing I didn't make a mistake, because I've never made a mistake before. 1.8 repeating. How fun. Now, what did you get for your decimal approximations? They're probably pretty close to these. You probably got similar ratios, you know, with accounting for measuring error. Now, how is that possible? Because we didn't have the same triangle. Maybe your triangle was like yay big. This little guy. Or maybe it went farther and was like yay big. Right? But however big it is, you're going to have different numbers here. Okay? But we're going to have same numbers here. Whoa, how do you get the same numbers from different numbers? Because of proportional ratios. Proportional sizes. If you had a bigger triangle, as your hypotenuse grew, so did your opposite. And they grew at a related rate. Sorry. As your hypotenuse grew, so did your opposite. And they grew at a related rate such that they maintained their relative size. Okay. Relative size is preserved for all right triangles with a 60-degree angle. Number 2. In the right triangle is provided, find the missing side length and then create the desired ratios. Alright. Pythagoras. What? Not 9 squared. That is 3 squared. Okay, minus 9. Oh, what? Did I do this right? 20. Oh, no. A squared, which is 9, plus b squared, which we don't know, equals 36. Subtract 9, 27. Square root both sides, and now this is square root of 27. That's annoying. 36 plus d, it's called d squared because this is opposite of the d side. Yes, we name sides of triangles after their opposite, because otherwise, how could you pick a side to name it? We couldn't call this the f side because maybe the hypotenuse should be called the f side, but you know what would always be the same as if we call it the e side. So d squared. That was. Don't worry if you didn't follow that. That's not important right now. That's for next year's math class. Bonus knowledge. 12 squared is 144. minus 36. 108. Square root of 108. Okay. For the little triangle, the opposite, what are we using as reference? A. Opposite of A is root 27 over the hypotenuse, which is 6, equals, what's root 27? .2. What's 5.2 divided by 6? Approximately 8.6. Okay, let's jump straight to the fun chase and go to the opposite and the hypotenuse. See this? Opposite and hypotenuse is this. Opposite hypotenuse for this other triangle using D as the reference is root 108 over 12 is the hypotenuse. Yep, 12 is the hypotenuse. And that is 10.4. And that is divided by 12. 0.866 again. Oh, 0.866. 6. Whoa, different numbers, same answer. Because of this special ratio. This ratio should get a name. Let's just check these other ones real quick. What's using A as reference, what's adjacent to A? A. I'm going to circle all the A's. A. What's adjacent to A? 3. What's the hypotenuse? 6. Okay, that's 0.5. Let's do this one. What's adjacent to D? 6. What's hypotenuse here? 12.5. Amazing. I want to pause for a second and say, we know these two triangles are similar because they have angle, side, proportionality. So they have an angle and then two sides that are proportional. Is that enough? I don't know. Let's just say there's just... I'm going to have to look it up. Bye. 1 second. Okay, I'm back. And no, of course that's not enough, but it's a 90. So using hypotenuse leg proportionality, we know these are similar. And another thing we can do is measure their angle. If I didn't drop my protractor, they would have the same angle. A and D are the same angle. Okay, I looked it up, and we're going to talk about it again in a second. After we do this last ratio, the famous opposite over adjacent. No hypotenuse involved this time. Root 27 over 3. Square root of 27 divided by 3. 1.73. Square root of 108 over 6. $1.73. Okay, here's the big reveal. This is a 60 degrees. And these numbers, 8.66, 0.866, 0.85. Huh. Oh, I messed that up. I did make a mistake finally. Okay. Haha, just kidding. Lots of mistakes, but hopefully good enough to follow. 0.866, 0.866, 0.85. Next one's 0.45. Pretty close to 0.5. Okay, that one's kind of off by too much, but it's still close to a half. I mean, given all the options, I'm in the ballpark. And lastly, 1.73, pretty close to 1.8. Because this is a 60 with a right angle, and these are 60s with right angles. So that we just did a bunch of similar. So what do you notice about the ratios from the two given triangles? They match. And compared to the problem number 1, they match-ish, because, user error with a ruler. What can you infer about the angle measures? They are all the same. $30, $60, $90. Why do the relationships you have noticed occurred? Is the next question. Because all those triangles are similar. So sides maintain proportionality. Measure the angles. No. We already did that. What might you conclude about the ratio of sides of a right triangle that has a 45-degree angle? Ratio of sides of a right triangle that has a 45? Well, they would match all right triangles with a 45-degree. And by they would match, meaning ratios of the sides. The ratios of the sides. They match all right triangles with a 45 degrees, no matter how big or small. Interesting. Oh, the ratios we worked with do have special names. Now, you know that I like to go over where these words come from, but this is a funny one because this is a mistranslation, and sine is from the Latin sinus, which means a bay, an open area, which is where our sinuses are open areas in our skulls where we can breathe through, and similar to a bay, which is an open area of ocean that you can sail through. But it has nothing to do with the mathematical term for sine. When it was originally developed in India, in Sanskrit language, and then taken through Persia, which is through Iran, through Saudi, through Babylonia. Well, no, not Babylonia anymore. What would it have been called? Oh, Baghdad. That's the word I'm looking through. Through Baghdad, which is near Babylonia, but different city, newer city. And finally to Europe, around the, I have to look this one, 11th and 12th centuries. So this is a worldwide phenomenon. Math is worldwide. We speak English, which is a European language, and so we use the European word for these things. But literally, the original Sanskrit word I don't know how to pronounce this. Kotija. Sine and cosine. In fact, the origins of modern terms sine and cosine have been traced back to the Sanskrit words ja and kotija. But those words in Sanskrit meant like bowstring. But then as it got translated and shortened in Arabic, and then the Europeans just said, oh, that must be the word for bay. But it doesn't really have anything to do with it. And then tangent. Tangent, I think, is different. We'll go over that later. But anyway, so these are the words we use for these ratios. They're names of the ratios. In fact, let's go back and label the ratios. This is the sine ratio, which short is spelled sin, but this is pronounced sine. This, yeah, and then adjacent over the hypotenuse is the cosine ratio, and is shortened to cos, but some people call it cos, but that's kind of tacky. I would call it cosine. And then tangent is the last one, which is shortened to tan, which a lot of people do say tan. So this is tan, this is the cosine, and this is sine. Specifically, this is sine of A. Since A is the reference angle, we found sine A. We found cos A, or cosine A, and we found tan A. Yes, very good. Now what are they doing? I think we're done. Have a fun time. Upload this. We're done. Nothing more. Upload now. Tomorrow, we'll do another most important video, number 2. And then we'll do the homework.